Lastly, we're going to cover the most efficient and most general sorting algorithm, merge sort. So let's start by talking about the key ideas behind the merge sort algorithm. Merge sort is a recursive divide and conquer algorithm, which means that at each step in the algorithm, we're going to split the array that we want to sort into two halves, a left and a right half. And we're going to sort each of those halves individually. Then, once those two halves have been sorted, a merge routine will take two sorted lists, each half the size of the final list, and merge them together. And by doing this for the entire array, what we end up with the end is a sorted full list. So in code, the way this works is we take a list we want to sort A, as well as an auxiliary array. This is important because merge sort, at least the standard way of writing merge sort, and the more efficient way, is to use a separate array, the same size as the original array, which we use to merge subarrays in separate recursive calls without trampling on each other. So this is not considered an in-place algorithm because it requires extra memory to run. We also take in a low and high that defines the region of the array that this call to merge sort is sorting. So our general routine is that we're going to compute the middle index of the array, just like with binary search, and we'll sort each half of the array separately. So each of these calls sort of makes our recursive leap and says, well, if we make this call to half the array, then when we get that, when that function call returns, that half of the array will be sorted. And then, assuming that that half of the array is now sorted, we then sort the other half of the array. Assuming that half is sorted, we then merge them together to create a sorted list. And this merging function is really the meat of the algorithm and what makes it work, is starting from recursing down all the way to a single element. You can think of it like we start at the bottom just with single individual elements, and we take those two elements and merge them together into a list of size 2. And then we merge those two lists together to a list of size 4, and then merge them to size 8, and then so on up until we've sorted the entire list. So to visualize that, here's a list with 8 words, and we want to put these in sorted order. So merge sort will recurse down to single elements where we're just sorting had and was. And then we want to merge these two lists of size 1 together. So had and was are already in order, so we keep them. Then we look at him and we sort these by merging them together. And him need to swap places, so we get and him. Then we take these two lists that are of size 2 and we merge them into a list of size 4, and him was, that is now in sorted order. Then we do the same thing with the second half of our full array. So we take his and you, we merge them together. Then we take the and but, and we merge them together. And finally, we take those two lists and merge them together to get but, his, the, you. And then we take this list of size 4 and merge it with this list of size 4 to get the final sorted list. Now try tracing out a merge sort run of your own. So given this example array, BACED, try showing the recursive merge sort tree, including what recursive calls are made, what array corresponds to each of those recursive calls, and what the result is from each of them. All right, let's start working through this algorithm. So first, we're going to split our array into two halves and call merge sort on each of those separately. So we'll start by finding the midpoint, which is 2, and making a call of sort with low being 0 and high being 2. That is going to make another recursive call, splitting this array containing B and A in half. One containing B and one containing A. Now, This call, first containing B, is our base case because the difference between high and low is now equal to 1. So there's a 1-element array. We don't have to sort it. It's already sorted. So that's our base case. We do the same thing with just the array containing A. And then we call merge, which merges those together into an array which is sorted. Now, we're not going to go into detail about the merge process, but for you, all you need to know is that this takes linear time in the size of the final array. So now we have our left half of the array sorted, and A and B are in the correct order. And we color these blue to say that this call now knows that its array is sorted because it has terminated. Up in our original array, we see that A and B are sorted, but we don't know that the full array is sorted, and we don't know that A and B are even in the correct positions until we have merged them with the right half of the array, which we'll show now. So the second half of the array, the right half, we'll make a call with low being 2 and high being 5, the elements C, E, and D. That will further break down into a left half containing C and E, and a right half containing D. Now for the left half, we're going to break that further down into an array containing C and just E. And each of those is one element, so they're sorted, and we merge them together to get CE. So now this call knows, that C and E are correctly sorted. And we're going to make a call on the right half, which is D. But D is already sorted. So then we merge them together to get the array C, D, and E. Now both the left and right halves of the top call have been sorted separately, so we just need to make one final call to merge them together. And we end up with our final answer, all the elements in sorted order. We'll wrap up our section on merge sort with a short Q&A. What is the worst case performance of merge sort? So think about the worst case and try and justify why that's the case. Let's start talking about its worst case performance. So the worst case performance of merge sort is always n log n. Regardless of the ordering of the array that you pass into it, it will always perform n log n in the worst case. So similar to selection sort, its runtime does not change depending on the ordering of the array. Whereas for a sort like insertion sort, if the array is in reverse sorted order, you get n squared. But if the array is almost sorted and small, it can look less than n squared. But merge sort generally always performs n log n. So the way it works is it creates this recursive tree where the top call and each subsequent call breaks the array down into two smaller halves. Those get sorted separately, and then it merges them back together. So in order to figure out what the runtime of merge sort is, we can visualize the recursive tree, as shown here. And then we need to ask, well, what is the height of the tree? And how much work is done at each level? So the tree has log base 2 of n levels, because every level we make 2 recursive calls that split the array in half. So the total number of calls it takes to get our array down to just a single element by dividing it in half each time is log base 2 of n. So the height is log base 2 of n. Now we think about how much work is done at each level. So at the top level, there is a merge sort call which merges 2 arrays that are each of size n over 2. So that merge procedure takes at most linear time. That's one of the properties of the merge algorithm. It's linear in the size of the final array. So the merge procedure at the top level takes n time because we have n over 2 plus n over 2 in the worst case. Now at each subsequent level, the same operation is being performed, the same merge, but the arrays are half the size. So for this left call, we're merging two arrays of size n over 4. That takes n over 2 in the worst case. But on the right side, we also have n over 2 in the worst case. So n over 2 plus n over 2 means n work done at this level. Then each of these 4 calls does n over 4 work, because they're merging two arrays, each of size n over 8. And this continues all the way down to the bottom, where there are n elements, and each of them does no work. Well, 0 or 1 work, depending on how you call it. Doesn't make a difference. But no work is being done at the bottom level, and there's n elements. So that means at every level of the tree, n work is being done. There's n elements at the bottom of the tree, so that's n recursive calls. And then at every level that merges elements, the sum of work across that level is equal to n. Which means every level does n work, and there are log base 2 of n levels. That means that the total amount of work is equal to log base 2 of n times n, which is n log n. And that wraps up our discussion of searching and sorting algorithms. I hope you found this video helpful, and best of luck on your exams.